Okay, I'm going to go ahead and get started. If you have questions, probably the best way is to put them in the chat. Um, if you want, you can also raise your hand and unmute yourself and ask. I am recording, so be aware of that. If you do either, you'll be in the recording. And I'll stop recording at the end to take questions if anybody wants to not be recorded. So today I'm going to talk about frequency distributions or probability distributions. But I'm going to start by talking about some of our assumptions about data, because this is why the reason that we are interested in probability distributions is to know the probability that something is random chance or not, and the reason that that's important is because or I guess that is one of our important data assumptions, is that they live under these distributions, but there are some other important assumptions that are related. And the assumptions themselves are important because we use data to make causal inferences. That is, to begin to make statements about cause and effect, inferring causes. We can't prove causes because everything is based on, reducing the probability that things are due to just random chance. And then there are other issues with cause and effect, like direction and confounding variables and lots of other things that, well, those are actually the two big ones, but other things that may interfere with establishing cause and effect with certainty. But statistics lets us take the random chance part and minimize it. So one of the things that we have to do in order to use data in this way is to make some of these assumptions. We're trying to make a model of the world that's abstracted. The world is too complex to just think about without taking some parts out. And so we try to look at as few variables at a time as possible. And there are different ways we do that based on these assumptions. This is like these models are like the idea of, if you wanted to make the perfect map of Texas, what would it be? Well, it would be the state of Texas, but you couldn't fold it up and put it in your pocket. So any map is an abstraction from the real world, and it's going to be imperfect because it's made smaller in order to make it manageable. And that's what our models are like. But these assumptions are useful approximations, even if they're not precisely true. So we can get a map of Texas that fits. We could get a map of Texas that would fit on, an 8.5 by 11 sheet of paper, and Texas itself is almost 1,000 miles wide. But the thing that would fit on a sheet of paper could get us from Houston to El Paso driving. At least if we knew where I-10 was, it could. So the models are the same sort of thing. They're how do we get to our end point from our beginning point? But we still need, and we make assumptions to do that, but we still need to check those assumptions to make sure that the real world isn't violating them in serious ways. So some of the assumptions we make are that data is random, that variables are independent, and that they're identically distributed. And that last part is related to the probability distributions. So randomness and independence matter as assumptions about data because they tell us, they let us see whether things are actually related. These are the things that we can look at statistically to see whether things are actually related, beginning to be related in a cause and effect way. These are assumptions about the data generating process, or the DGP. So the data generating process doesn't mean the way we collect the data. It doesn't mean something that happens in the computer. It doesn't mean something that happens about our observations. It doesn't mean, well, it may mean whether we did an experiment or not, but ultimately the data generating process is the world. It's the real world. All of our data comes from real human behavior. It's the way that the world produces it. And that process, the main thing we know about that process is that it's stochastic. You're not going to see that in the slide, but that's the word. It's random. The big word for the day, the one that you can impress graduate school committees or whatever with, is stochastic instead of random. It means exactly the same thing. So that's data comes from this random world where things are not always predetermined. They're not, there are variations that we can track, and they're at the base level. We can eliminate a lot of them. A lot of them are not random, and we can eliminate those if we've got sufficient data. But even if we have all the data, there is still some degree of randomness, especially with human behavior. So that's one of the reasons, aside from the fact that it's complex, so there are lots of variables in human behavior, one of the other reasons that it's tougher than the physical sciences, because gravity is not random. It's pretty much the same everywhere. The rules apply. Human behavior is not like that. Humans do funny things, sometimes for no reason at all. The second thing that we know about our data generating process, or assumption, is that all variables are independent and identically distributed. This is called the IID assumption, which is why I'm putting them together, but they are actually two different things. The independence just means statistical independence. And what that means is that our X variable, we assume going in that X is not related to Y. So for example, if I do one coin flip and we call that observation X, and the second coin flip and we call it observation Y, which we normally wouldn't do. We would normally call the first one X1, the second one X2, or something like that. We would put them in a column of X's, but if we call one X and one Y, they don't affect each other. There is some recent physics research showing that maybe they do affect each other. So we'll go with a little different one. That's the usual example, but since it's arguable, I'm going to go with a little different example. Let's say that I want to randomly assign people in the room to groups. So I first have everybody draw a number out of the hat, 1 through 4, for the rows in the classroom. And then for each row, there are, I think, 10 seats on the row. So I have everybody on each row roll one of those 10-sided dice that you use in, well, I don't know if anybody even plays it that way anymore, but Dungeons and Dragons or role-playing games that are played on a tabletop, they have 10-sided dice. So it's just like your normal 6-sided die, except it's got more sides. So it's got numbers 1 through 10. Well, the hat draw doesn't affect the value of the rolling of the dice. It doesn't matter whether you are on row 1 through 4. The die roll is still going to be random. It's not affected by the other. It doesn't. The hat draw. Say that you draw 3 on the hat, that doesn't affect our belief about what's going to happen when you roll the dice. Like, we don't think, well, you drew 3 on the hat, there's no way he's going to roll a 3. Well, yeah, there's a 1 in 10 chance of rolling a 3. It's the same for everybody, no matter which row you're on. If we start talking about variables where we're talking about cause and effect, of course, if X causes Y, they're going to be related. They're not going to be independent. But we start with the assumption that every variable is independent from every other variable. And the result of that is that if X does affect Y, or if there's a relationship between X and Y, if we improve our chance, if knowing something about X makes it easier for us to determine the value of Y, makes it easier for us even to guess the value of Y, if it affects our belief, then we can begin to infer that there's a causal relationship going on. We can't prove it, and we don't know what the nature of the relationship is, but if knowing X tells us something about Y, or if knowing Y tells us something about X, then they're no longer independent, and we begin to think that maybe cause and effect is going on here. It may be cause and effect through an additional variable, or even more than one additional variable. So we might have the shark attacks and ice cream sales that we can predict shark attacks by ice cream sales. We can begin to infer there's a causal relationship. Realistically, there's a third variable. It's probably temperature. And it's probably that it gets hotter in the summer. So that's the additional variable. But we can at least, even if all we have is the 2, we can sit there and begin to say, why is this happening? Is there a causal relationship? It also may be completely random, like the case of the Nick Cage, in years that more Nick Cage movies are released, there are more swimming pool drowning deaths in the United States. There is something seems to be going on there. Probably if we run the statistics, we would find it's just the result of random chance. It probably isn't causal. And so that's one of the things statistics does for us that we're going to use those frequency distributions for. We don't know which direction the causal relationship goes. Even if we know that temperature correlates with shark attacks, higher temperature, higher shark attacks, we don't necessarily know without theory and without something else to establish it, which way it goes. Is it increases in shark attacks make the weather hotter? Probably not. Is it that hotter weather makes people go to the beach and there are more shark attacks? That's probably what it is. So there again, there's a third variable. Hotter weather makes people want to go to the beach. They go to the beach, they're more likely to get attacked by sharks. We need theory, and then we'll need something else to establish what other variables are going on and what direction. So it's not necessarily that X causes Y. It could be that Y causes X, or that something else could be going on. You have probably heard this not quite accurate summary of this. Correlation does not imply causation. A lot of people say that. That is actually incorrect. And I'm not the only one who says it's incorrect. Steven Pinker, the psychological linguist and famous author, also says correlation does, in fact, imply causation. It doesn't answer all these questions for us, and it doesn't prove causation, but it does imply it. It tells us there's something going on there that we should look at. If it's of interest to us, it tells us here's something we may be able to investigate. And that's what imply means. It doesn't prove it, but it does imply it. So this is all about that independence assumption. The independence assumption would tell us there's not going to be a relationship between ice cream sales and temperature or shark attacks. If there is actually a relationship, that tells us something's going on, because it means that in the real world, the assumption didn't hold. The next is that these are identically distributed, which means that our variables, or our variable, every draw of the variable comes from the same probability distribution. This does not mean the X and the Y have to come from the same probability distribution. It means that every draw of X. So if we're rolling dice and we're calling it X, every die has to be a 10-sided die, and it has to be a fair 10-sided die, not 10-sided on one roll, 6-sided on another roll. They all have to be the same so that we're drawing from the same probability distribution. If everybody's drawing from the hat, everybody has to draw from the same hat, and it has to be with replacement. Somebody draws row 3, we have to put the piece of paper back in, mix everything up so that the next person has the same chance of drawing row 3. So the identically distributed means they come from the same probability distribution. And so that's where we're going to get into distributions. Distributions, these are frequency distributions or probability distributions. So we can draw them, and when we draw them, it's usually a frequency distribution to start with, which means that all we're doing is counting how many times each result happens, and then plotting it. R has functions for at least 20 probability distributions. We're not going to use them all in R. We're definitely not going to use them all otherwise. We're going to have one that is going to be hugely important and a couple of others that we need to be aware of. But we're mostly going to use the normal distribution. And since we're mostly going to use the normal distribution, that's one of the reasons for why I told you the type of variables you need for those projects. So the most important one is the normal. This is also because of the central limit theorem, which we're going to spend a chunk of a day on, but I'll talk about a little bit today, a little preview, and because of the law of large numbers, which I'll also talk about later. These are the ones we're going to look at in the most detail. The normal, because we're going to use it the most, and it's probably, it's if not the most important, it's definitely one of the most important in political science research. 10 years ago, I think you could, well, 20 years ago, I think you could have said it is far and away the most important. The binomial and some others have become more important. So normal may not be in the majority anymore, but it's still probably the biggest use. The binomial, we're going to look at that. We're going to look at the uniform distribution and Poisson, and we're not going to look at them in order because I'm going to start with the uniform. The important thing here is that these are probability distributions, so they allow us to determine the probability that some event that we see in the real world is random chance or not. And when we get to hypothesis testing, we'll also be able to use the probability distributions to determine whether the relationship between X and Y is random or not. So these examples, these are histograms. Like I said, these represent the frequency. That is the number count of observations for each value. So if I show you one of these, it may be for 100,000 draws, and it shows you how many times each number occurs. So if it shows a value If the value of 4 shows 500, that means 4 came up 500 times in the data. And sort of a preview here, if it's 100,000 draws and 4 shows up 500 times, then we could say that the probability of 4 is 500 divided by 100,000. That's pretty small, right? That's if 500 divided by 100,000 is 5 in 1,000, which is 1 in 200. So it's it's 0.5% chance of a 4. If I did I think I actually did that math in my head right. So, so these graphs were all produced by generating random numbers based on the particular frequency distribution with an R function. And I have the code in here for how I did that, so that you can refer back to it. I'm not going to go through it today though, but it's in the slides. So later, if you want to produce something similar, which there may be good reasons for, you'll have the code to do it. So the uniform distribution is just the distribution where all outcomes are equally likely. Drawing from that hat where there are rows 1 through 4, if it's truly random, if we shake it up well enough between every draw, every outcome is equally likely every time. Everybody has a 1 in 4 chance of drawing 3, 1 in 4 chance of drawing 1, 1 in 4 chance of drawing 2, a 1 in 4 chance of drawing 4. This is the simplest distribution. And if you think about it, it's uniform. Think about what the histogram for that is going to look like. If every number has an equal chance of happening, it's going to be pretty flat. And in fact, with 100,000 random draws from 0 to 10, this is what it looks like. And it is pretty flat. It is, all of them are right around 10,000. And, they are, so they're, so 5 had almost exactly 10,000. 1, 2, 3, 4, 5. Yeah, 6 had, it looks like probably a little under 10,000. 7, 5 might actually have been a little higher. 7 is probably right at 10,000. The variations here are just the random fluctuations, the simulated random fluctuations of the draw. So for any one of these, so for 10, it's roughly 10,000 out of 100,000, or 1 out of 10. For 9, it's, maybe 10,100 out of 100,000. So it is slightly more than 1 out of 10. But for the actual distribution, it is 1 out of 10. And what is the actual distribution? Well, it's if we did this as we approach an infinite number of draws, this gets flatter and flatter. And so were we able to draw an infinite number, it would be perfectly flat. We can't do that. But as we approach infinity, it gets flatter. And all these deviations are just random deviations. And we can know that by how far they are. If we came in with something that we thought was a uniform distribution, but the 1s and the 10s were way lower, that would tell us, wait a minute, this isn't a totally random uniform distribution. There's something else going on here. And what might that something else be? It might be that we have a normal distribution, because normal distributions are not perfectly flat. The normal distribution is a distribution that's symmetrical around the mean. So that means it's equal on both sides. and most values are near the center. The width of the distribution is a function of the standard deviation. So that's why we needed to know the standard deviations. So bigger standard deviation, the more spread out around the mean it is. Smaller standard deviation, the more bunched up it is. So when I said that if I think earlier, a couple of times earlier in the semester, that if I know the mean of the height and I know that it's 5'7", and then I know the standard deviation because that's in original units, probably in inches, then I can begin to visualize what the classroom looks like. And if I assume it's a normal distribution and I know that standard deviation, then I can begin to actually even visualize not just how tall the average person is, but how many people are 1 or 2 inches shorter, how many are 3 or 4 inches shorter, and what the extreme is going to be. Like, what is sort of the maximum? Like, who's going to be the shortest and tallest in the room? I can begin to make extremely educated, not even guesses, but calculations about. They're not going to be perfect because we're still random. But if something doesn't fit my calculations, I can begin to say, wait, something's maybe going on that's not random. Other names for this. So if you hear me say Gaussian, you probably won't, but if you do, that's what we're talking about. But this is a cocktail party thing. You can impress people by talking about the Gaussian distribution, and then when they ask what you're talking about, you can say, oh, you probably call it the bell curve. That's the other name for it. More importantly, if you get into a more advanced stats class, or you start talking to some professors and they use this, it is important to know, I mean, as you get more advanced in your work, that somebody may call it the Gaussian distribution. So you've seen this before, I'm almost certain. Probably at some point someone has shown you this with regard to curving a test result. Or you may have seen this with particular pieces of data. It's called the normal distribution. That leads a lot of people astray. It does not mean everything is distributed this way. I just showed you the uniform distribution. Those die rolls from the 10-sided die, if all we're doing is recording them and we don't do anything else, that's a uniform distribution. Coin flips are a different distribution that we'll get to in a minute, called the binomial. An individual coin flip is called a Bernoulli. So it's normal, but that doesn't mean it's everything. And so people who are confused by this include, so there was a high school stats teacher who should not have been confused by this, who did a 6-hour video after the 2000 election, in which he claimed he proved that the election was stolen, but he assumed that votes are normally distributed. Votes are there is no reason to assume that votes are normally distributed, and in fact there's good reason to assume they're not. So he came in with this normal distribution idea, and people were spreading this around the internet. Half a dozen people sent it to me, and they were using the word incontrovertible. Here's incontrovertible proof. And I didn't watch the whole 6 hours, because in the first 15 minutes, I knew he was making bad assumptions about the distribution of votes, because in the entire first 15 minutes, this guy is just talking about normal distributions, and not everything is normal. What is the normal distribution? So it is symmetrical around the peak, so it drops off pretty much symmetrically in each direction. And again, this is 100,000 draws. and its width is a function of the standard deviation. So in this case, I told R that I wanted a normal distribution with a mean of 0 and a standard deviation of 1. And as you can see, it drops off, and that standard deviation of 1 tells me pretty predictably that by the time we get out to -4 and 4, there are not very many observations out of this 100,000 draws. That means also that the probability is a function of the standard deviation, because it's symmetrical with the width as a function of standard deviation. Then the probability of 2 standard deviations above or less should be the same as the probability of 2 standard deviations below or more. And how do we get that? Well, if I want to know the probability of 2 standard deviations above or less, all I have to do really would have to do is add up these, all of these, right? Each one, add them all up, these numbers, the counts, and divide by 100,000. If I wanted to know the probability of 2 standard deviations below the mean or more, I would do the same thing. And again, because it's random, we've got some variation. But as we approach infinity, we actually know what those should be. And we don't really even have to get that close to infinity for us to draw some meaningful statistics. We don't even have to get close to 100,000. We need to get to maybe 100 is really good. If if we know the underlying distribution is normal, then we can start to draw inferences with actually as little as maybe 30 in our sample. So the big implication for this, and it's not just an implication, but it's a mathematical, it has been proven. I'm not going to do the proof for you, and I'm not going to make you learn the proof. But we know that 68% of the occurrences are going to occur between 1 standard deviation below the mean and 1 standard deviation above. 95% of the occurrences are going to occur between 2 standard deviations below and 2 standard deviations above. That 95% is going to turn out to be our gold standard for statistical significance in the social sciences and life sciences. If we go out to 3 standard deviations above and 3 standard deviations below, that's 99.7% of occurrences. And the hard sciences tend to use either 99% or 99.9% as their standard for testing hypotheses, for figuring out if something is statistically significant or not. So for us in the social sciences, 2 standard deviations is really important. 2 standard deviations above and below. We're going to translate that into something called a z-score, and we do that. The actual number is 1.96, but if you can remember 2 and -2, those are hugely important. And 1.96 is so close to that if you can remember 2 and -2 on an exam, I'm not going to give you 1.96 and 1.97. 1.96 may be one of the answers. The other answers are going to be far enough from 2 that you should be able to get it. So remember 2 standard deviations above and below the mean are going to capture 95%. And what if we want to capture, just going one way or the other? Well, it's a little more complicated, but we can still do that. if this is 95%, well, actually, what we can do is, if this is 99.7%, is everything in here, and so we want to know everything below here, it's going to be 99.7 plus this, which is going to be 0.15. So everything below here would be 99.85. If this is 95% and we want to capture everything going this way, this is 95. This is 95, but there's another 2.5% here, 2.5% up here. So it's 95 plus 2.5 is 97.5. So for any number, we can figure out either direction as well. Slightly more math if we do it by hand. Not anything really extra at all if we do it with R. Maybe typing something slightly different. So this is hugely important, and it's the 68, 95, 99 rule, or if you want to be really specific, 68, 95, 99.7 rule. So the next one's the binomial distribution. This is a binary distribution. So if we want success or failure, yes or no, heads or tails. Heads or tails is the classic example that we can actually simulate, right? Because we could actually do a number of these trials. This isn't the distribution for if I do 100 heads or tails. That's a Bernoulli distribution. A binomial distribution is the distribution for a certain number of Bernoulli trials. So here, if I do one trial of 100,000 flips, I put draws, it should be flips. So 100,000 flips of the coin, one trial, and it's a fair coin. So I set the probability equal to 0.5, 50-50, 50% probability of heads, 50% probability of tails. Then my distribution with 100,000 draws should be 50,000 heads, 50,000 tails, or something very, very close to that. Now, the important thing is, so this is with your standard fair coin, but I can adjust this probability. So there are some Bernoulli examples where, what's the probability a country goes to war in a given year? If we know nothing else, we can still look historically, and in most years, countries don't go to war. So the probability of a yes going to war is going to be much lower, like a 0.05 or something, which means then if we see a country going to war, if we see countries with certain characteristics going to war 10 times as much as that, we can begin to make inferences that some shared characteristic of those countries may be causing them to go to war more often. So, but we can vary the probability. This is one trial, but, and that's because I set n equals to one trial. It's not because there are 100,000 draws. It's one trial with 100,000 draws. What if I do 25 trials of 100,000 draws? And so these numbers are not the individual draws. They're the sample mean of each trial. So I have 25 trials of 100,000 draws, and it looks like the average of the averages is about 15,000. And then there are about, there are 15 trials that have an average of 10,000. There are 16 trials that have an average of about 7,500. There are 19 trials that have an average of less than 1,000. And oh, look, it's symmetrical around the mean. What if I do a whole lot of trials? What if I do 1,000 trials? Oh, it's beginning to look, at 100 trials, it's beginning to look kind of bell-shaped. And at 1,000 trials, it's beginning to look awfully normal at 1,000 trials. And this gives us a preview of the central limit theorem. The central limit theorem is going to tell us that for sufficiently large sample sizes, the distribution of the sample means approximates a normal distribution. This applies to lots of different underlying distributions. So what the central limit theorem does is allow us for most, if not all, I think the claim is all, I'm not necessarily 100% convinced of that, but for most, if not all, underlying distributions, something like this is going to happen. That as we get sufficiently more trials, the average of each trial, and we make the average of each trial an observation, the distribution of those averages is going to start to look like a normal distribution. Means with a large enough number of trials, we can begin to apply the normal distribution to know things about the measures of central tendency, the measures of dispersion, and the probabilities for most things, for things other than things that are normally distributed. Now, the key is we have to do a large enough number of trials. If we only do one trial, we need to work with the underlying distribution. If we can do a sufficient number of trials, we can begin to look at it with the normal distribution. And what is a sufficient number of trials? Well, for many distributions, 30 trials is sufficient. So sample sizes above 30 become important because of that. That's just a preview. The other rule that we get from these distributions, the one I showed you, the 68, 95, 99.7 rule, is for the normal distribution. 68% of the data is within one standard deviation of the mean, 95% is within two standard deviations, 99.7 is within three standard deviations of the mean, and we can begin to apply that to things that are not normally distributed through the central limit theorem if we have a sufficient number of trials. The third thing I'm going to give you a preview of that is related to those two in terms of more trials giving us better results is a preview of the law of large numbers. The law of large numbers tells us that if we repeat an experiment a large number of times, the average of the results, so the mean of the results, is going to be close to the expected value. So the expected value of a coin toss is neither heads nor tails because it's 50-50. The expected value of 10 coin tosses, if we make it in terms of heads, the expected number of heads on 10 coin tosses is 5. If we only toss a coin 10 times, the probability of getting exactly 5 is not 50%. It's considerably less than 50%. If we do 1,000 coin tosses, there's going to be a really good chance that our average result is going to, and actually if we do 1,000 coin tosses and we do it, well, if we do 100,000 coin tosses and we do it 1,000 times, the chance that we're going to get that 500 becomes really, really high. And the chance that we're going to get between 500 and 520 is somewhere around 68%. That's central limit theorem, but it's related to this law of large numbers. If we repeat an experiment a large number of times, we're going to get close to the expected value. And the expected value of something is just the outcome of interest times the probability that it'll happen. So the expected value of a lottery ticket is the probability of winning times the value of the ticket. So the Powerball's paying $100 million cash value, and the probability of winning is 0.000000001%. I don't know if I did the right number of zeros. The expected value of that lottery ticket is something like 30 cents. That's what an expected value is. And the law of large numbers tells us if we repeat it a large enough number of times, we're going to get an average of 30 cents for our Powerball tickets. How many times would it have to be for the Powerball? Well, to get the expected value, you would have to buy enough tickets that you win at least once, because otherwise you're going to be way below the expected value. So that number for the Powerball tickets, you'd have to buy hundreds of millions of them to get there. For other things, you don't have to get as high. For most experiments, it doesn't require anywhere near that large a number. What this does, this allows us to take the sample mean, the sample standard deviation, the sample variation, and apply them to the population. Because if we know the distribution, we can apply the mean of the sample, and we can use it as an estimator of the population. So we can use the sample statistic, the sample mean, to determine the population parameter, the expected mean of the population, if we have large enough sample size. And since the variance and standard deviation are a function of the distribution and the mean, we can do the same with the other statistics. Okay. So this is where statistics and parameters come in. So a statistic is a measure that's calculated from a sample of the data. So the sample mean, sample variance, sample standard deviation, those are statistics. A parameter is the same number for the population. So the population mean, population variance, population standard deviation, these are the parameters. And we use the statistics as unbiased estimators of the parameters. So I think we're down to the last or next to last. Yeah, this is the last distribution. The Poisson distribution. I did not put this in here just to demonstrate my inability to pronounce French words. I put this in here because it's important. It's especially important, those of you who may want to use some count variables in your own data work to understand exactly why we can't just apply the normal distribution. For our purposes, for demonstration, it's fine, you can, but you'll want to include a note in your work that, hey, this is actually a Poisson distribution, this is probably not correct, or this is probably not exactly correct. What is a Poisson distribution? It's a count of the number of events in a fixed time and space. So the specific application of this was to Prussian cavalry. The first time this was done was figuring out Prussian cavalry, excuse me, Prussian cavalry, trying to figure out how many horse kicks would happen in a cavalry unit in a year in a certain region. So it's got to be in a fixed time and space. So if you have the number of horse kicks in Prussia in cavalry units in a year, that's going to be a Poisson distribution. It has a known constant rate of occurrence. So in this case, if we know that horses kick at a certain known rate, there's a certain percentage rate at which horses are going to kick. We use that to determine it, that. And you're thinking, well, if it's a known rate, then we just multiply them, right? Well, no, because it's a random world. So it's a distribution. If the rate is 1%, 1% of horses are going to kick somebody in a year, and there are 100 horses in the unit, that doesn't mean just 100 times 1, because it could be, well, first of all, with 100 horses, it's possible we have a horses who kicks 10 times as much and could just totally throw the numbers off because the world is random. There are also, there are all kinds of random things that could happen that could go into this. The second thing is, though, that the kicks have to, the whatever it is, the occurrence has to be independent of the time since the last event. So it's the chance that any particular horse is going to kick this year has to be independent of whether they kicked last year. And in fact, whether they're going to kick today is independent of whether they kicked yesterday, other than the known constant mean rate of occurrence. So this is a Poisson distribution with 100,000 draws. And I gave it a lambda of 1. And what is lambda? Lambda is the mean and the variance. So one of the unique characteristics of the Poisson distribution is if it's a I don't want to use the word normal. If it is a standard Poisson distribution, is that the mean and the variance are equal. And in this case, I set the mean and variance at 1. And it turns out that the difference between 0 events and 1 events is very small, but it trails off. It trails off pretty quickly. So if someone's doing research on war, and I told you don't use is there a war or not, because that's binomial, but you can use battle deaths as a variable. Technically, those battle deaths are going to be a Poisson distribution, but the battle deaths are also going to be such a large number typically, because the definition of war is usually a minimum of 500 or a minimum of 1,000. So the number of deaths is going to be sufficient that you're probably going to be able to apply the normal distribution and get away with it. But you should be aware that's not the distribution here. It's 0 to whatever, and it drops off. It drops off pretty rapidly in a standard Poisson distribution. What are some assumptions? Well, first of all, the proper probability is different than the normal distribution. Why? Well, look at it. I mean, the probability is there's a very high probability of a 0, a 40 out of 100,000 probability of a 0, 40 out of 100,000 probability of a 1, or something like that. I guess probably 35 out of 100,000. And then a 20,000 out of 100,000, or 20 out of 100, 20% for a 2. But then for a 3, it's very low. It's not symmetrical. The normal distribution would head out to the left. Lambda is both the mean and the variance of the distribution. If we get away from that, then the dispersion, it's over or under dispersed, is the phrase. and we start having to look at there are alternative distributions in that case. We don't generally use standard deviation with Poisson. I can't recall anybody really talking about it in any Poisson stuff that I've seen. We don't need it because with the Poisson distribution, lambda gives us what we need to find the probabilities. We don't need the standard deviation. It doesn't. It's not laid out like the normal, where the standard deviation is what we use to get the probabilities. So the probabilities in that example, in this coming example, are specific to this setup with a lambda equal to 1. And this, what I'm about to show you, is why count variables should not strictly be done with the thing we're going to learn starting in a week or two, ordinary least squares regression, which is the linear regression technique we'll be using. It's the most common in political science. And it doesn't technically work with Poisson distributions because it's based on normal distributions, at least as far as hypothesis testing. So with this lambda equals 1, so that these probabilities don't work. If we change the lambda to something else, these are not the right probabilities. But with lambda equals 1, 70%, 74% of the outcomes are below 1, are 1 or below. 92% are 2 or below. 98% are 3 or below. The 4 or below are going to be like 99.5% or something. And when we get out to 5 or 6, by the time we get out to 6, it's just virtually 100%. There are some observations for 7 or 8, but they're so small they don't even show up on the histogram. So that obviously doesn't look like the normal distribution. We base the likelihood of something being significant, that is 95% not due to random chance, on proximity to the mean. As things get further from the mean in a normal distribution, they become less likely. In a Poisson distribution, it's as they get further from 0, or whatever the base is, but usually 0. So we apply OLS to sample means of multiple trials because of the central limit theorem with the normal distribution, but we have a better technique with Poisson, which is to use the underlying distribution. So here's the normal distribution. It's symmetrical. The Poisson is not. So now I'm showing you a Poisson with a lambda equal 1, right? And a normal distribution with mean of 1 and variance of 1. So, which means it would also be a standard deviation of 1. So it's 1 for the means and the variances on both of these, but clearly the probabilities aren't the same. If I want to get 97.5% with the normal distribution, and then 98%, practically the same with the Poisson distribution, at first glance, it looks like they're the same. But then when you realize, well, wait, no, because the normal distribution includes a lot of numbers. It includes about 30 plus % of the numbers are going to be negative. Well, those don't exist if you're talking about a count. The lowest count for something is 0. So we get right here at 1, where the mean and the variance and the standard deviations are all 1. We get close to the same count, but the Poisson is still a higher count. At 0, the Poisson count is much higher, and below 0, there is no count. but the normal distribution tells us there's something like a 32% chance that the number is going to be negative. And you can't get negative horse kicks. The horse is not going to reach out with its hoof and go, I take it back. It doesn't happen. 30% are negative, and that's just not even possible. So it throws off our numbers. Out here, it also throws them off quite a bit. So there's more of a chance of a 4 with the Poisson, even though it's a very small chance, it's still higher than the chance with a normal distribution. Because the chance with a normal distribution out here of being out here is less than 0.3%. Whereas with the it's in fact way less than 0.3%. So significant difference. An important difference between these distributions that we can't ignore. So that is it for this lecture. I'm going to stop recording and I will answer questions. Give me a second because I have to figure out where my stop recording went. There it is. Okay, there we go.